Yeah, so it's our pleasure to have like Nicholas to share his work with us. Like today, he'll be sharing with us like how we can learn like mixed states using variational kernel algorithms. Um, yeah, I guess I could pass the floor to you, Nicholas. You can start your talk.
Sure. Yeah. So thanks for inviting me. Yeah, as introduced, you can also just call me Nick. I'm a PhD student at the University of Southern California. Although the work that I'll be discussing today on the titles here, quantum low rank approximation and mixed state compiling, I basically did as an intern at Los Alamos National Lab. So I wasn't formally associated to the LANL Quantum Summer School. But for all intents and purposes, I interacted with all those people. So that's how I ended up working with these people that you might recognize from potentially being at LANL. Basically my intention, oh wait, okay, yeah, there we go. So my intention is to talk for roughly 45 minutes to 50 minutes and leave the rest of the time for questions. But as I was already mentioned, feel free to ask questions in the middle. Probably, I think it was mentioned that you can just type it in the chat. That's fine. And oh, whoops. Yeah. So one thing I wanted to share in the beginning though was what works am I going to talk about? So the first work will be, you can find in this archive, is the low rank approximation problem. And the second work actually coincidentally was published today in Quantum Science Technology. And you can find it here. And since this is a variational quantum algorithm, on a personal level, I think it's important to also just share your code that gives every detail of exactly what you did. So you can also find that here. It's a GitHub repo, but you can cite it with something called Zenodo. Okay, but that aside, my goals today will be to basically tell you what the title means, of course, and show that the quantum mixed state compiling is sort of a natural follow-up to this low rank approximation. And then to give you enough information that you can either implement our algorithm, or at least some idea of how to implement it, or you can use our code. And if you're someone that isn't interested in using the algorithm, because this is a specialized audience, I want to go into enough methodological detail that you may find something else interesting or useful for your own work that isn't using our particular algorithm. So part one is to discuss this first part of the title, what does this mean? And I'm going to start with something very basic, but mainly just to establish my notation. So I'll consistently throughout the talk be discussing some target density matrix rho. And I'm going to assume that my eigenvalues are ordered. There's no reason not to do this. It makes things convenient. And I'll often refer to its rank. And don't be confused. I'm not talking about the Schmidt rank. There's no bipartition. I'm literally just talking about the rank in the matrix sense, the number of non-zero eigenvalues. And the notion of a low rank kind of comes up naturally when you just start considering mixed states of real physical systems. So for example, if you consider a low temperature thermal state, then the support is primarily over a small low energy subspace. And so just as some example, I'm considering this thermal state of essentially an XY model chain, although I'm allowing the coefficients to randomly change. But regardless, if I consider just a very simple 3-qubit version of this chain, then it commutes with ZZZ. And so we might expect that the ground state is doubly degenerate. And indeed, that's true. And if you look at a low temperature, so beta equal 20 in this case, if you compute the spectrum of this Hamiltonian for randomly generated values of J and K, then you pretty much always get essentially 1/2, 1/2. And that's equal probability to be in either of the ground states, and something very small for the rest. But formally speaking, this matrix exponential is full rank for all for all finite values of beta, right? In other words, the first order term is the identity. So you can't get over the fact that these are still just, exponentially small, but non-zero values. But, that's no problem, right? We can just define something like an effective or epsilon rank, which is to say that I should sum up the eigenvalues from 1 to k and find the smallest k that makes this sum epsilon close to 1. And this is a very natural thing to do, because if you consider the truncated matrix formed by just summing up from I equal 1 to this epsilon rank, then it's epsilon close to the original density matrix in trace distance. So it's the right definition to be close in an operational sense. And so to me, that kind of made me wonder a few sort of natural things, where natural is kind of, arbitrary thing to say, but it's just something I wondered. The first thing is, well, this rho epsilon is technically speaking not a valid quantum state since it's not normalized. So it's what the closest valid quantum state is, and namely to solve this minimization problem. And relatedly, I might instead of asking what the closest sigma is to rho epsilon, I might just say, well, forget about truncating. In the beginning, let's just solve the problem from the very beginning, which is to say, which is the closest sigma to rho, where sigma satisfies a rank constraint. And then finally, whether these two things agree when I choose, the rank constraint to be consistent with the epsilon rank. Okay, so you might say, well, if I have a truncated matrix and I want to make it normalized, well, I'll just do the thing that everyone always does, right? Just renormalize it, no big deal. By some standard renormalization. But it turns out that this choice, while optimal for trace distance, is not optimal for the Schatten P norms. And so I'll rigorously define the Schatten P norms in case you've forgotten about them, but they're just basically the vector norm of the singular values of the matrix. And it turns out, though, that if you instead renormalize by what I call an additive normalization instead of a multiplicative, where you add a constant epsilon over d to every diagonal element of this matrix. So essentially, you're adding a constant to every eigenvalue of the original truncated state. Then this is optimal for put the laser pointer. This is optimal for all p values. So by the way, that does in fact mean that the optimum for the trace distance is not unique. So the fact that both of these are optimal for trace distance, it is the case that it's not unique. But it is unique for p greater than 1. But just to sort of codify what all of these, what I've been talking about by a simple example, let's just say that I've diagonalized rho, which is fine to do, right? I'm always I can always do that, and I can just talk about the spectrum, because these definitions are really about the spectrum of rho anyway. Let's just say I know the spectrum is this three-dimensional state as this spectrum with, and I've chosen my tolerance epsilon to be 0.01. Then for this example, the epsilon rank is 2, and the truncated state, or in this case, the truncated vector, would just be to remove the final eigenvalue. And I can check indeed that the difference between the two vectors is almost trivially epsilon by construction. And furthermore, if I renormalize this truncated vector by a multiplicative or additive renormalization, the distance is still equal to epsilon as expected. But if I try to do this for the two norms, say, if I do the multiplicative one, it's slightly bigger than the additive renormalization. And this leads us to the related question, which is, well, what if I just try to tackle the original optimization, where I just say, what is the closest rank constrained state to some arbitrary state rho. And like I said, P norm is now defined for you in explicit detail. It's basically the LP norm of the singular values, where the singular values are the eigenvalues of this matrix here. For P equal 1, you have the trace distance, as I've been saying, and for P equal 2, the distance, as I may have also have said. But before discussing the quantum solution, it's worth to point out, especially to a machine learning community, that this is very close to a famous problem, a classical low-rank approximation problem. And in particular, when you choose the 2 norm, which is classically known as the Frobenius norm, but for us, Hilbert-Schmidt, and you drop the trace constraint, then you can just see that you can actually find the solution on Wikipedia even, in something called the Eckert-Young-Mirsky theorem. And the solution is to project your state onto what's called the principal components. So this projector, because these eigenvalues are ordered, this is essentially saying I'm projecting onto the eigenvectors associated to the R largest eigenvalues. And these are, again, called the principal components. And so the final state would just be this truncated state. And so you might not be surprised, based on how I've presented things, to learn that the quantum solution is the classical one, so this truncation, plus an additive normalization, contrary to what you might expect being the multiplicative renormalization. And again, as we've seen, this is unique for P greater than 1, but one of many highly degenerate solutions for P equals 1. And so just to kind of see an example, let's consider that we have a state which has 3 eigenvalues. So it's a 3-dimensional Q-trig, if you will, and we want to approximate it by a qubit. So a 2-dimensional density matrix. Then the solution should be the intersection of the trace normalization, which is to say that lambda 1 and lambda 2 have to be equal to 1. So that's this blue line, as well as the minimizing distance itself. So for the trace distance on the left, the contour of equal distance is a square, right? So the unit ball is a square for the 1 norm. And so the intersection of this square and this line, of course, is an infinite set of points along this line. Whereas the solution we've discussed before about this additive renormalization is only this single point in the middle. But in the Hilbert-Schmidt distance, where the unit ball is an actual ball, then the intersection is just meeting at a single point. And so that's what I mean by it's unique for, for example, P equals 2, but not for P equal 1. And in this interpretation about principal components, this is bad for trace distance, in the sense that notice that to the left of this point, lambda 1 is greater than lambda 2, and to the right, it's the opposite. So that the relative ordering of eigenvalues and eigenvectors is not preserved when you're minimizing the trace distance. So if you minimized it to find the first principal component, you're not guaranteed that you're actually getting the thing you expect if you when you do something like principal component analysis. Okay, so I also asked a third question, which is whether the 2 notions that I've discussed about truncated states agree. And of course, I wouldn't expect you to have followed every epsilon from the talk so far, but it turns out they don't agree, because the additive renormalization we first talked about produced a full rank state, right? Because we just added the identity. Whereas the solution of the quantum low rank approximation is, this added normalization to a subspace, right? So we can preserve the rank constraint. But there is kind of an easy way to make them agree that sort of makes sense, which is if I just solve the quantum low rank approximation problem where I plug in rho epsilon instead of rho, then you get what you expect. And the bottom line, without following every line, is that the notion of truncating to R epsilon and getting some sigma, rho epsilon is consistent with the solution to the low rank approximation problem when you constrain the rank to be R epsilon. So in other words, the solution to this problem is the appropriate thing to think about when you think about a low rank truncation of rho. And because, like I said, beyond just the ideas themselves, I wanted to give some idea about the details so that if you run into similar problems, you at least know what kind of things I was thinking about when I was proving these results. But actually, a lot of these results may be familiar to you, and if not, the ones I used weren't super right. They're just kind of so it was new to me as a physicist, say, but the ideas were just convexity and convex optimization. The new part being majorization and sure convexity, and then I used the Minkowski inequality and some properties of unitarily invariant norms. And so, in terms of the first bullet point, if you want a good reference, you can use this book. But really, there's some lecture notes of a course that it talks about this book from Princeton. The first few lectures are sufficient for the information I needed. And then I used this very nice book on inequalities, theory of majorization and applications to learn basically all the inequalities and things I needed to know about majorization. And recently I've been reading Bhatia Matrix Analysis, which kind of more pedagogically introduces these ideas. Although at the time, even this second reference was sufficient. But the basic idea of the proof is the following, right? So here's the problem we were trying to solve. We wanted to, and by the way, right, so now that I've introduced the idea of convexity, this is a non-convex problem. Why? Because when I add a rank constraint, the convex combination of two density matrices, of course, can have a rank bigger than R, right? So you don't necessarily expect to find a nice solution, but these tools allowed us to find one anyway. So the first step is just to assume that rho is diagonal. Nothing stops us from doing that, but if for some reason you want to be really, really precise and you're not comfortable with making any assumptions or whatever, although this is completely fine. Oh, this is a unitarily invariant norm. So first I'll pre-process by the thing that diagonalizes rho. But whatever. Given that rho is diagonal, then we can parameterize sigma, this unknown vector at this, or unknown density matrix at this point, by just saying, okay, it's some unitary transformation from the basis that makes rho diagonal, and the eigenvalues, I'm calling them mu I, are supported over some set where this set, the number of, this support being the eigenvalues greater than 0. This support has to be smaller than R, right? Or smaller than or equal to by the rank constraint. And then you can just say, okay, let's first break this down to optimizing over U's. And what you find is that the U that will make this thing minimal has to be a U that's just a permutation. But if U is a permutation, then this is now no longer a matrix minimization, it's just a vector minimization. Because now rho is diagonal and sigma is in the same basis. Or up to a permutation, right? So it's still a vector. And now you have a vector minimization. And well, I have some of the details here, but actually just to make sure I have time, I'll save this until the end, or in case people have questions about it. But the bottom line is that you can use some ideas about majorization and one nice trick in order to find that the solution turns out to be what we expect. So you truncate the vector lambda onto the principal component subspace, and you make an additive normalization to make up for the loss of the thing that to make this of sigma equal 1, basically. Okay, so I've spent a lot of time talking about this low rank approximation, which technically isn't the mixed state compiling paper that I was asked to talk about, but you'll see that they're very related. So, but now let's talk about this mixed state compiling. Okay, so first let's at least kind of vaguely state the goal of mixed state compiling, which is so I've been talking about this target rho, but let's make it a bit more concrete and say that rho is on some quantum computer. And if you'd like, we could just say that you've applied some circuit to a set of qubits. And due to both noise, which I'm indicating with these red lines, as well as the fact that the final state you're interested in may be on a subset of the qubits, then tracing out this, you'll result in a mixed state, right? But even just noise is enough to give you a mixed state anyway. And our goal will be, okay, given this rho. Oh, was there a question?
I didn't see any questions. Yeah, I think you can continue for a moment. Yeah.
Sure. So then given this rho, the goal is to find a circuit to prepare low rank approximation we've been discussing. Because of course, you can always choose R to be equal to the rank of rho, in which case you're finding a circuit which prepares rho. But in a way, it's more interesting if you are looking for an algorithm which can also find the low rank approximation. And of course, as a special case, it's finding the circuit to prepare rho. Okay, so why would we want to do this? Well, the first reason is that the low rank approximation, say we choose a state like the thermal state, where the epsilon rank is much less than the technical rank of rho. But that means that this truncated state will be, or rank reduced state is still epsilon rho. So if you want to do some experiment, it's sufficient to use this one with a much lower rank. Well, the much lower rank state as a circuit requires fewer resources to store. Because as we'll discuss, you can store a mixed state as a probabilistic combination of bases of pure states, in which case we're saying you only need R epsilon pure states instead of the potentially much larger rank of rho pure states. But alternatively, you might want purification of the mixed state, in which case you need fewer qubits to generate a purification, which is epsilon close anyway. So one is it requires fewer resources to store this reduced rank state. Second, just kind of as an interesting query in and of itself, so far I told you that the explicit solution to the low rank approximation problem, strictly speaking, requires you, or at least naively speaking, requires you to diagonalize rho, because I'm telling you, you need to project onto the subspace with the largest eigenvalues. But in order to know that subspace, naively, you would need to diagonalize rho. But if we formational algorithm, then we'll find out you don't actually need to do that. You can find a circuit to prepare the low rank approximation without formally solving the hard problem of diagonalizing rho. And it follows sort of almost directly from what we said already, but just as to specifically highlight it. When you find this circuit, you're essentially getting the, even if you find the low rank sigma R, and R isn't large enough to be a good approximation like in bullet point 1, well, you're still getting the R first principal components of rho. Namely, you're getting a circuit to prepare these eigenvectors with the largest eigenvalues. And so in a way, it's a way to do PCA on a quantum state. And then finally, you can think of it just as a different way to think about learning a quantum state, where as opposed to, say, state tomography or shadow tomography, because in these approaches, you're ultimately looking for a classical description of a quantum state. And in the case of state tomography, it's the matrix elements. For shadow tomography, it's some expectation values that then allow you to estimate other expectation values. But either way, it's a classical description. In this case, we want to learn a quantum circuit. So all the description which you can then use on a quantum computer. So you can think about it in any of these ways, depending on what you want to do with the final state. And just to be slightly more concrete to what we're discussing, and then we'll go more and more details. What I'm thinking about is that after I have rho on the quantum computer, I append some parameterized quantum circuit. In this case, I'm saying that I have a 2-qubit, say, state rho, I want to learn say the first two principal components, then all I need is a single qubit, and I can apply rotations to this qubit in order to kind of intuitively unprepare rho. And I'll be more precise about that. But the bottom line is that I want to find this quantum circuit will somehow encode enough information for me to generate my guess of the state sigma. And in this case, it's thinking about it as a convex combination of pure states. And just before I give all the details, I just wanted to show some sense of what all variational algorithms follow a similar formula. You have some parameterized quantum circuit, you feed it to a classical optimizer in order to reduce some cost, and then the hope is that in a reasonable amount of iterations, the final cost is low and that you found a quantum circuit to do the job that you want. So in this case, I'm saying, okay, I have a state. I want to learn a state, just like I've shown before. I can run classical numerical simulations to see how well this procedure works, or I can run it on actual quantum hardware. But at this point, you don't know what the cost is and everything. But the thing I want to drive from this slide is that whether I do classical numerics or I run on real hardware, the final angles I get that somehow encode the state I learn and the probability, the two things that define my mixed state are roughly pretty similar. But now this is just kind of some data, but you don't know what the things are. So let's go. Actually, I'll skip the slide. Let's define all the things that make up our variational algorithm so that we can understand plots like this. So to any variational algorithm, of course, not just ours that we're going to discuss. I mean, obviously you need an input and an output, but you also, in this case, will need a cost function, some ansätze, a classical optimizer, and a verification metric that somehow the thing you got at the end is working. And for us, the input will be the quantum device in the state row. So that's what we've already established. The output will be a circuit that prepares your best guess for the low rank approximation. And we'll be more precise about what the circuit actually is. The cost function will be the squared Hilbert-Schmidt distance. And you'll also want, in some sense, some sort of local variance to try to avoid barren plateaus. We'll discuss that very briefly. Then you need an ansätze. And in our case, we actually need kind of like two ansätze. So one is an ansätze for how to upload a mixed state to a quantum computer. And then the other is for the actual circuits themselves. But let's just talk about sigma first. So we can either encode it as a purification or a probabilistic combination. We'll say exactly what these things are in a minute. The classical optimizer, so this is, for most variational algorithms, you kind of just try and practice, empirically what optimizer works well for you. You can either build up your own optimizer by hand, or you can use some sort of black box method. In our case, we found that just the black box method, Powell, works pretty well. This is a non-gradient based method, but the actual optimizer itself, depends on your particular variational algorithm. And then finally, in terms of verifying that the solution we get works, well, typically the cost, in a lot of cases, their verification comes naturally because when you finish the algorithm, the cost becomes zero when it succeeds. But in our case, since the hopes would not go to zero unless you're learning a full rank approximation, then we will have to use the solution of the quantum rank low rank approximation to verify things. Again, we'll discuss this more. Okay, so first let's discuss our cost function, because in general, you want any cost function you use in a variational algorithm, just as a general principle, you want it to have several properties. The first is you want it to be easy to compute on a quantum computer. If it's not, then there's no hope that the quantum computer is a tool to use to solve your problem. And as we'll show, this is actually easy to compute. The second thing is that you should hope that whatever it is you're evaluating should be conjectured to be hard to do on a classical computer. This is also true for our cost. And roughly speaking, it's easy to compute on a quantum computer because you don't need to diagonalize rho minus sigma. And roughly speaking, it's hard on a quantum computer because you do. I mean, sorry, on a classical computer because you do. Again, this is kind of rough, but that's kind of the intuition. And then 3, you hope to find a local variation of this cost, which is essentially evaluating the cost as you hope, and that the cost vanishes in the same conditions. So they both, when the optimization finishes, they both find the right solution, but that the local variant prevents a vanishing gradient. But in our case, this turned out to be way more difficult than we expected for mixed states. And so the details are actually kind of complicated, and I'll point you to Appendix A in our paper. But the bottom line is that we weren't able to find a local cost for a generic mixed state. Now, it may just be our lack of ingenuity, but it would also be quite interesting if we could prove, although we were unable to in this work, to prove that there is no local cost for the Hilbert-Schmidt for mixed states. But we were able to find a local cost in certain special conditions. So if your state is pure, it works, but we already knew that, right? So that's kind of just referring back to previous works. But you can extend this idea of the local cost for pure states to high purity states. And then we were able to define a different local cost, which works for tensor product states, which are not necessarily pure. It's like sigma 1 tensor sigma 2, which we could then slightly extend to low entanglement states. But again, a generic local cost precluded us, and that is one, say, issue with scaling our algorithm. And we hope either that can be found, or it would also be quite interesting if we could prove that no local cost exists for this function. But probably more importantly to an audience which knows some things about quantum information, before I go to that. So those are the 3 things you would want for any variational algorithm for your cost function. And in our case, it also has the desirable property that it has a unique low-rank solution, which is necessary for things like PCA. Whereas if we were doing trace distance, it wouldn't be unique. Although, of course, these other things wouldn't be true either. And then finally, and this is an important point, which actually I'll just skip to the next slide. There's sort of an elephant in the room for this cost function if you're an experienced quantum information theorist, because you probably know, or if you don't, I'll tell you that a quantum information theorist would argue that the Hilbert-Schmidt distance is not good for state discrimination. But basically, I'm using it in that way. So you might say, okay, what's going on? And in case you're not privy to this idea, let me give you an example of why this might be the case. So let's say that rho was had a uniform distribution of eigenvalues on the left side of this support, and sigma has it on the right side. And of course, I'm talking about the left and right side of the support. So let's just say the dimension is even, so I don't have to worry about odd. So what happens in the middle? So d over 2 of them over here and d over 2 of them over here. Then the trace distance is maximized for these 2 states, which makes intuitive sense because these 2 states should be distinguishable. They don't have overlapping support. So there should be a measurement, namely the measurement which distinguishes this fact, that tells us that these states are orthogonal, more or less. But if you compute the Hilbert-Schmidt distance, then it's 2 over square root d, which goes to 0 asymptotically as d goes to infinity. So you're in the situation that these states are perfectly distinguishable, and yet the Hilbert-Schmidt distance is very small. And more generally, this is captured in this inequality that the trace distance sits between the Hilbert-Schmidt and square root d Hilbert-Schmidt. And again, this kind of tells you that if Hilbert-Schmidt is very small, that does not imply trace distance is small, because there's this factor of dimension hanging in front. Whereas the converse is true. If trace distance is very small, we know Hilbert-Schmidt is small. Okay, so there has to be some sort of fix, or I wouldn't have, or I would be nefarious and hide this complaint from you, right? So it turns out, okay, this bound that I showed you with square root d in front is actually much tighter for low rank states. So, okay, I've been talking about low rank states in a sense this whole time. So, thank goodness, right? There's some hope. And this, when I say it's much tighter, the square root d essentially becomes 2 square root fancy r. And this fancy r is the reduced rank. So this, if you took, say, classical mechanics and you learn about, celestial motion or even the hydrogen atom with the electron, you encountered the reduced mass. But here, instead of mass, we're talking about rank. So it's the product of rank rho and sigma divided by their sum. And this tightening of the bound has the nice property that, by the way, if I choose rank rho and sigma to be the same, both the same and equal to 1, so they're pure states, then this inequality becomes an equality, which is what we expected, because this whole dimension factor isn't an issue for pure states. No one ever has an issue with distinguishing pure states with Hilbert-Schmidt. But it also has the nice property that if at least one of the states is low rank, so let's say sigma is much lower than rank rho, then the reduced mass becomes the smaller rank, which by this assumption here is much, much lower than the dimension, which means we're not cursed by this factor of dimension in front of the right-hand side of the inequality, and that as a low Hilbert-Schmidt for a low rank state should imply a low trace distance. So if you're interested in this inequality and this tightening of this bound, refer to this paper from 2019. But it saves the day for us because in one sense you could say, okay, our algorithm works for low rank states. In another sense, you could say that you can use our variational algorithm for a low rank state and successively increase the rank and seed. Say you learned rank R, you can learn rank R plus 1. Where you start in the local minimum generated by the rank R. But regardless, I would be fine to say if you left the talk by saying, okay, it works for low rank states, and you may run into this factor of d dimension problem for when both states are high rank. Okay, so that was kind of a digression, but I think it's important. But now we've defined our cost and we've justified it in a few different ways. The next thing we have to define is the actual ansatz. So the most sort of intuitive way to think about a mixed state is maybe how you learn it in the first place, which is that it's a probabilistic mixture of pure states. And an easy way to generate such a mixture is to, with probability pi, prepare mixed state U acting on basis state I. So basically I have a fixed unitary U of theta. And if I act on it by different computational basis states, it prepares different orthogonal states psi I. And I can just simply sample these probabilistically as the input to my algorithm. And so I'm never preparing the entire mixed state at once, right? I'm just sampling it probabilistically by pure states. But this is sufficient, for example, to compute expectation values where I could just randomly sample my input, do trajectory-based time evolution, or again, to do PCA, because in the end, once you've optimized this ansatz, these psi i's will be the principal components of rho. And okay, so by the way, okay, you might say, okay, when R is low rank, then I can store the PIs no problem. If R is large rank, you have to be more clever about how you store the PIs. If there are exponentially many of them. And there's ways to do that we discussed in the paper, but for now, let's just say you've stored them classically. In which case, this next part will make sense. So what we want this ansatz to not only encode our state, but allow us to compute the cost efficiently on the quantum computer. And the cost broke down into 3 terms, right? The purity of rho, the purity of sigma, and the cross term. Well, the purity of rho doesn't matter because it's constant. And so for an optimization, we don't care about its value. The purity of sigma, of course, does matter, but it's just the sum the squared sum of these probabilities, which you can just compute classically, or if you have too many of them, you can do this something called a classical swap test. And it turns out the classical swap test is also necessary for the cross term, which you can show that it's equal to this. So namely, you have rho on your quantum computer, you apply U dagger, and then you make a measurement and you see what bit strings you get. And then you weight those bit strings with probability pi. And you can see Appendix B in the paper for more details about this. But the quick summary of what this is that this expectation value also defines essentially a probability distribution, Q of I. And then the expectation value of the indicator function that you get by asking whether the bit string, okay, well, let me explain this way. So say that I and j are random variables sampled from P and Q as distributions, and you define this chi as 1 if I and j are equal to each other and 0 otherwise. Then the expectation value of this indicator function is an unbiased estimator of this sum of probabilities in this way, which of course is equal to the trace of rho sigma. And you only need a polynomial number of samples when your error is additive error epsilon by the Hofting inequality. So I guess if it's hard to follow the details, the main point is that when you want to estimate quantities like this, product of two distributions, you can use something called the classical swap test, which comes from defining an indicator function and then applying Hofting's inequality. But perhaps what will be simpler is just to describe the alternative, which is to prepare sigma as a purification. So instead of thinking about a probabilistic ansatz, let's just prepare, take the circuit and apply it to D1 plus D2. So in this case, the D1 system, or the dimension D1 system, is our system of interest, and this dimension D2 system is ancilla qubits, say. So if you want, D2 is 2 to the k for k ancilla qubits. Well, when you trace out the ancilla system, the resulting density matrix for randomly initialized values theta for some circuit, well, this density matrix will generally be rank D2. So it'll have the rank will be the same dimension of the ancilla system. And so you can prepare a rank D2 state by applying a unitary on, say, a D1 dimensional system and a D2 dimensional system and tracing out the D2 dimensional system. And this purification has the same applications as before, but in addition, you can use the purification to compute things like entanglement measures or the Ullmann fidelity and symmetry measures, which require the actual purification and not just the classical ensemble of states. And this quantity or this ansatz allows us to compute the cost efficiently as well, because this cross term that we discussed before can be evaluated with what's called a swap circuit, or its destructive variant, which is essentially, the destructive variant is actually almost simpler to describe. You prepare rho on half of your system, sigma on the other half. In this example, I'm just doing a single qubit just to make the circuit small. I apply a C0 between them and then a Hadamard and then measure all the qubits. But the n-qubit generalization is just, it's a Bell measurement. So you just apply a chain of C0s as if you were preparing a GHZ state and then a Hadamard. And the resulting measurements on all the qubits, you can relate this to this trace rho sigma. And for a single qubit, it's just related to the probability that the output is 1, 1. And for the swap test, I won't really explain it for now, but you can see all the details. We actually derive, this is a known result, but I derive it in the paper just for posterity, that if you measure this ancilla qubit in the circuit and you compute its sigma z expectation value, then it's equal to this. And we also provide an alternative circuit called essentially a Loschmidt echo approach. But anyway, you'll see that, especially in this example, that you only need, so say you have an n-qubit state, you need n C0s and a Hadamard, So you need, only O of n gates to compute this object. And then the post-processing, the number of measurements you do, again, by the Hofstadter inequality will be polynomial. So you're never dealing with, something intractable. You have polynomial number of gates, actually O of n, and, some reasonable measurement. So this is easy to compute on a classical computer, or sorry, a quantum computer. And it's conjectured, as most complexity theory results kind of are, it's conjectured to be hard on a quantum or a classical computer to compute this cost function. Okay, so then finally we have all the ingredients in a sense, but now we need a way to test whether the cost value we get after optimization is close to the optimal one. And so in general, this optimal cost, you couldn't compute it easily, but in our examples, we'll be able to compute it exactly by the low rank approximation solution. And what this looks like in practice is this, right? So we have a desired state we want to learn. In this example, it's a 7-qubit XY thermal state. And what you do is let's say we learn a rank 1 approximation, so a pure state approximation. Then our optimization goes, and at some point it kind of converges to something and it stops. So this C theta star stops and converges. And then we can compute the optimal possible C, and that's this horizontal dotted line. And we just compute the difference between these two things, right? Not too complicated. And we can increase the rank of our approximate rank state. And you see that, for example, when we learn a rank 4 approximation, well, that's almost good enough to be, this state is effectively rank 4, say, with a very good small epsilon. And what we can do as a verification is we can generate random states according to some distribution. And in this case, I'm talking about these random XY thermal states. So they have random coefficients J and K. And we can plot this delta for different learned ranks, say, and just kind of empirically observe, how well we're doing when we learn different rank approximations. And so we can also ask a related question, or take this verification metric, which kind of summarizes how close we got to the optimal solution, and see how it looks as we increase the number of qubits when we learn a low rank approximation, and also how many iterations it takes. And I guess, looking at these box plots may not be the most intuitive thing possible. So I won't keep on and on going about them. But the bottom line is that the thetas are very small. So even though they grow, we're still talking about 10 to the minus 7 on the left-hand side. And if we look at the number of iterations it took us to reach that solution, it's way smaller than what it would take to naively do tomography to learn rho, like all of rho and then truncate. And the same or something similar happens even when we learn the full rank approximation empirically. The deltas are not quite as good, but we still require way fewer number of cost function evaluations than we would need to compare to tomography. And in order to, one detail that you actually have to specify when you try to do this algorithm empirically is, well, I keep mentioning that, for example, the ansätze is that you apply some unitary u of theta. But this u of theta should depend on your problem. And you actually have to think about it, what's the appropriate u for your problem? And for the XY thermal states, the short answer is that you can choose a u that preserves the symmetry of your states. And when, it turns out we choose a u that does that, which requires us to do log n depth circuits that requires only roughly n log n parameters. And, so that's pretty good. But that's because we exploited the symmetry of our problem. And I guess, you can also, I said this thing, the solution to this thing is also used for PCA. So here I'm just kind of illustrating that a little bit. And I guess, based on time, I'll just say that the bottom line is that when you learn this low rank approximation, essentially you you can just look at the overlap between the first eigenvalue or eigenvector you get and the fidelity between it and the actual eigenvector of rho. And if you're learning principal components, it should be that the fidelity is very good. And as you see, the infidelity in this example for an effectively rank 2 state, that you learn the first 2 eigenvectors very well, which is to say that you have the first 2 principal components that you want. And you can also think about this algorithm as a way to estimate the effective rank of your state by learning increasingly smaller rank approximations and finding the lowest rank that you need to have a small cost. But given the time, I guess I'll skip this example. This was just an example on actual hardware where we learned states which were generated by noise. So we don't even know what the original circuit was. So that's kind of an interesting one where you don't, where it's kind of like tomography. But for now, let me just conclude to say that we defined a notion of approximate state rank. We defined and solved the quantum low rank approximation problem, which is very related to this. We developed a variational quantum algorithm to try to solve this problem as well. And then in practice, somewhat surprisingly, you have to use the 2 norm, at least if you care about things like PCA. And it turns out that that's okay. That you don't have to be quite as worried about it from this, sort of information theory thing we discussed about. And with that, I'll leave you the references, and I guess in case there's any last questions, I'll stop talking.
Yep. Thanks, Nick, for the nice talk. I found your talk very informative, especially you show all the references that you use to prove your results. So far, I didn't see any more question from the floor. Maybe I could ask the questions while people thinking what question to ask. Actually, I do have a questions about the last point that you mentioned here. So do you have an intuition of why the 2 norm will preserve eigenvalues ordering? Because it's crucial for doing PCAs, right? But I didn't, as in from the first part of your talk, you mentioned that for 2 norm, the Hilbert-Smith norm, if you give you unique solutions for low quantum low rank approximation problems, but how why would they kind of preserve the eigenvalues ordering in this case? Yeah, just wondering.
Yeah, so in this for this, it might be easier to just go back to this plot that I had before.
Yep.
So basically, the intuition is that, well, one intuition is you can just ask what if the unit ball has any lines. So in the case of the 2 norm, it's an actual ball, so it doesn't have any lines. So the plane or line in this case of eigenvalues or of normalization, basically. So this line is like the line of normalization. Will only cross at a single point. Whereas for trace distance, because the unit ball has lines, then they can cross at an entire interval. But that's sort of a geometric thing. But if you're asking, a different way to think about it is from basically thinking about the proof a little bit. And basically, when you think about the vectors, the vector for the state sigma, the vector of eigenvalues, has to be normalized, right? So basically, it's saying that this vector, but normalization is the same thing as saying that the 1 norm is equal to 1.
Right.
So if you're minimizing the 1 norm subject to the constraint that it's equal to 1, you actually have a lot of flexibility. The constraint doesn't do anything. Whereas if you're minimizing the 2 norm, or actually just p greater than 1, subject to the constraint that the 1 norm is equal to 1, then that's an actual constraint. And when you combine the constraint with the desire to minimize, then you get a unique solution. And a final way to think about it is actually kind of if you have some intuition about majorization,
Yeah.
then majorization is essentially like the study of wealth inequality, right? So when you basically, the one norm, you can change wealth around. So if I give you some of my money, then the one norm can be preserved, even if I give you some money. I'm exchanging the eigenvalues basically. But if I give you some money and I think about the two norm, then because I'm squaring, then it's like x plus delta x. Well, the square now, it's no longer going to be preserved, the two norm.
Right. Okay. I see.
But yeah, I guess it would be easier with pen and paper, but hopefully that
yeah. It's in like, yeah, it's like, it's kind of nice that you'll be able to like to give like 3 different ways of looking into the same things, and yeah, kind of like get the hang of like why it is so. Yeah, so we still have no question. Maybe I just like ask another questions. Recently, like people are more and more like interested in to studying the dynamics of quantum systems, right, using like quantum machine learning. And from here, I can see that you can like learn the row rank approximation of a given Benson matrix. And I'm just wondering, like, if you evolve this low rank Benson matrix, row rank approximation states with some union trees, and then compared it with the original state, the evolved like original state, how will the error propagate? Do you kind of like
I see.
Yeah. Because over here you kind of like constrain yourself to be low rank, and there will be some errors on the states like kind of like epsilon distant away from the original state you want to approximate. But then if you kind of evolve these two states, and how will this error propagate? Yeah, just wondering, will it be constant, or you kind of explore yeah.
Yeah, that's a good question. I haven't thought about it, so I'll give you my guess. So let's see. So unitary, well, it can change the basis, but it's not going to change the rank of my state.
Okay.
So my guess would be that it stays the same, the error. But if I think about it from the unitarily invariance of the norm, then I guess it's not quite obvious that that's rigorously true, but my intuition would be that it's true. But I have to think about it to give you like a more careful answer.
Right.
But that's a good idea to think about.
Yeah, because yeah, I saw like a lot of people's, like, for example, Joe is also like considering like how to study like quantum dynamics using quantum computer and stuff. So just like thinking of like how this thing will behave if we consider your protocols like to basically compress the set and stuff.
Yeah. Thanks for the question. I'll definitely think about it.
Yeah.
I see.
So yeah, we have a question from Daniel. Maybe Daniel can just like mute yourself and
Thanks for the interesting talk. So I was wondering about the two norm. You said that it can still be useful if you're trying to approximate your state with a constant rank state.
Yeah. So this was this discussion around here. Yeah.
So I'm just wondering. Suppose you want an approximation which the rank is growing exponentially with the number of the system size, but still it's a low rank compared to the full exact state. I guess then this reduced rank is not going to be so useful. Can you think of a way around this? I'm asking this in the context of like dequantization algorithms where you may want a state with an exponentially large rank in order to avoid an efficient classical algorithm.
Yeah, so I would say that so basically this factor would be square root of this exponentially large quantity, but that is still exponentially smaller than d, right? That's what you're saying, right?
Yes. Yep.
So naively, if you just implemented the algorithm where your input to the algorithm is an ansatze for that rank, then I wouldn't expect it to work, or I wouldn't have high confidence that it would work, although it may just work anyway, right? I mean, that's always possible. So in some sense, the only way to test it is to actually just try it. But the way that I've thought about it around it is to essentially intentionally learn smaller rank approximations first. And so let's say you first learn, say, some constant value rank. So you learn a rank, even just a pure state approximation first. So if you learn first a pure state approximation, then this inequality actually becomes an equality and there's perfect harmony. And so whatever you learn should be, if you get a small Hilbert-Schmidt, you also get a small trace. And then if we're thinking about the ansatz as a convex combination, then you can start you can then run the algorithm where you learn a rank 2 approximation, where your initial parameters for theta can just start with the local minimum you found for rank 1. And I think that would have a higher chance of working. But actually, when I was originally, well, okay, I'll say I haven't thought carefully about how to ensure that it works when you care about high rank states, but that's the first idea I had about it. But I haven't rigorously tried to get a sense of when it would extend to high rank. But that's my guess about how, like, an effective strategy where at each step you're doing something that made sense based on a lower rank approximation. Of course, in terms of your application, where, of course, incrementing in steps of 1 wouldn't be a good idea, right? Because you want to get to an exponentially large one. But I guess this is kind of in a sense, the nastiness of all variational algorithms is that there are always some heuristic, right? You kind of hope they'll work for your application, but at the end of the day, you just have to try it and see what happens. And I guess if you go and look at this paper, I think they numerically explore how well, in a sense, you could say this bound is somewhat perhaps it's pathological, and that you have to cook up examples like this to make it terrible. And you can just numerically generate random rho and sigmas and just ask, how often is this bound actually, that far apart? And I think they did something like this in this paper and found that it's not always that bad, right? So in that sense, for if your states, it turns out just, this is pathological and your states are actually much better, 2 norm is way closer to 1 norm than you might expect, then I guess you don't even have to worry about this low rank, because it's already good enough, I guess, is something else to think about.
Thanks.
Yeah, thank you.
Yep, I think now the time is like past like 12 past 6 on my side, and I think it's 9 past 6 on 6 minutes on your side. So I guess like we can kind of end the seminars here. And if the audience have any questions, I guess they will just like email you, and like you can just like reply the email to answer the question and stuff. Yeah. So like Nick's like has put his emails in the chat, so like if like you guys can take a note on that and drop an email to Nick if you have any questions. Yeah, thanks again, Nick, for like giving this like informative seminars on your work, and I found the resources that you kind of like mentioned in the proof kind of useful to learn and to study and apply to other programs. Yeah. Okay. Thank you very much.
Yeah. Thanks again for inviting me, and yeah, feel free to reach out by email, and have a good day.
Yep.
For everyone.
See you.
Yeah.
Bye.
Yeah, bye.